Hi class, we continue our study in chapter 7 talking about similarity by moving into section 7.4. And this section is just about proving triangles are similar. So we have two objectives in this section. First, we want to use the what we call AA similarity or AA similar, angle-angle similar postulate, and the SAS, which we know is side-angle-side similar, and SSS, side-side-side similar. So I've been saying similar, that's what this squiggly line represents. We learned that last section, theorems. And then finally, we want to use similarity to find what we call indirect measure. Okay, so let's start by talking about what the angle-angle similarity postulate is. So if two angles of one triangle are congruent to two angles of another triangle, actually what that means by extension, the third angle is also congruent, then the triangles are similar. So if you look here, we have this triangle and this triangle. If the corresponding angle S is congruent to its corresponding angle M, and corresponding angle R is congruent to its corresponding angle L, then we can say that triangle SRT is similar to triangle MLP. So all you have to do is show that two corresponding angles are congruent, then therefore the two angles are similar. All right, so let's look at this. Determine whether triangle RSW, right here, RSW, and triangle VSB are similar, and let's explain. All right, so by studying the diagram, we can use the angle-angle postulate, angle-angle similarity postulate. So what we have to do is show two pairs of angles are congruent. Right off the bat, we can see that angle R and angle V are congruent because both of these measures, both these angles here measure 45 degrees. But then what we want to do is talk about angles 1 and 2. Well, it looks like they're vertical angles. So angle 1 is congruent to angle 2 because vertical angles are congruent. And so we can say that triangle RSW is similar to triangle VSB by the angle-angle postulate. All right, let's determine whether triangle JKL and triangle PQR are similar. And let's explain that as well. Well, looking at the diagram, we see that we can use the angle-angle postulate, angle-angle similarity postulate here. So we want to show two pairs of angles are congruent. So first we see that angle L here and angle R here both congruent are both congruent, and they're corresponding angles for the similar triangles. They both measure 70 degrees. Well, what we see here, we want to show measure of angle K and measure of angle Q are congruent. So how we find the measure of angle K here, it's 180 minus 30 minus 70. Well, that's 80 degrees. Measure of angle P here, that's 180 minus 85 minus 70, that's 25 degrees. So just by looking here, K is not congruent to Q. J is not congruent to P. So only one pair of angles here is congruent. So triangle JKL and triangle PQR are not similar, because you need to show that two angles are congruent. All right, the side-angle-side similarity theorem. So side-angle-side similarity, right? This is what this squiggly line represents again. So if an angle of one triangle is congruent to an angle of the second triangle, and the sides that include the two angles are proportional, so that means the proportion of their sides are congruent, then the angles are similar. So here, if we look at side AB and side QR, and that's congruent or equal to side AC divided by side QS, and the included angle between those two are congruent, then we can say that triangle ABC is similar to triangle QRS. All right, so AB to QR has to be equal to AC to QS. All right, then we have the side-side-side similarity theorem. So if the corresponding sides of two triangles are proportional, then the triangles are similar. So again, if the ratio of AB to QR is equal to the ratio of AC to QS is equal to the ratio of BC to RS, then we can say that triangle ABC is similar to triangle QRS. All right, let's tackle the problem. So determine whether the triangles are similar. If they are, let's write the similarity statement for the triangles. And we either want to use the angle-angle similarity postulate, the side-angle-side similarity theorem, or the side-side-side similarity theorem. All right, so just by looking at these triangles here, it looks like we're given the lengths of each side. So right off the bat, that's going to tell me I want to use the side theorem. All right, so we want to use the side lengths to identify corresponding sides. We want to set up ratios for each pair of corresponding sides as well. So here I have the sides in color here that are correspond to each other. So ST and VX, UT and VW, and US and WX here. So first off, let's start with the red side. So ST, the ratio of ST to XV is 6 to 9, which simplifies to 2 to 3. Then we'll look at the longest side, the hypotenuses. So US to WX is 10 to 15, which simplifies to 2 to 3. And then the remaining sides here is TU and VW here is 8 to 12, which simplifies to 2 to 3. So all their ratios are the same. So all three ratios are equal, so corresponding sides are proportional. So we can thus say that triangle STU is similar to triangle XVW by the side-side similarity theorem. All right, let's do another one here. All right, determine whether the triangles are similar. If they are, let's write the similarity statement and use any of the theorems that we have. Okay, so here what I want to look at is I have this triangle KMN, and then I have this inscribed triangle KLP. Right, since we have included an angle K here, right, let's try using that side angle side similarity theorem. So I want to show this side, this angle, and this side here. All right, so we can say angle K is equal to angle K by the reflective property of congruence. So I want to show then that the ratio of KL to KM is the same as the ratio of KP to KN. So let's look at that KL to KM, as I said. Well, that was 8 to 10, which has a ratio of 4 to 5. And then finally looking at the KP to KN, that has 12 to 15, so that has a ratio of 4 to 5. So we can say then that triangle KLP is similar to triangle KLM by the Sideangleside similarity theorem. All right, let's move on and talk quickly now about indirect measures. So sometimes we can use similar triangles to find lengths that cannot be measured easily. So we use this indirect measures to find such lengths. So I got this one example here. Before rock climbing, a student wants to know how high he will climb. He places a mirror on the ground and walks backwards until he can see the top of the cliff in the mirror. Right? What is the height of the cliff? So here's what we see. He has to walk 6 feet, and he has a height of 5.5 feet. And then we have this other triangle here that has length here of 34 feet, and then height x here. So what we're going to say here is basically that the ratio of 6 to 34 is going to be the same as the ratio of 5.5 to x. All right, so we can use proportional sides if the triangles formed. Triangle HTV and triangle JSV are similar. So since the angle of measure T and the measure of angle S here are both 90 degrees, what we can say is the measure of angle HVT here is equal to the measure of angle JVS, right? Since the light reflects on and off the mirror at the same angle, right? So we got this angle and this angle here are the same. So we can say then if two angles are congruent, we can say that triangle HTV, this one, the small one, is similar to triangle JSV by that angle-angle similarity postulate. So we got to set up a proportion then to find x here. So H to T is the same as J to S is equal to the ratio of T to V to S to V. So just plugging in like this, right? 5.5 over x is the same as 6 over 34. Cross multiplying here, 5.5 times 34 gives me 187. 6 times x gives me 6x. Divide by 6, you get roughly 13.2. So the cliff is a little over, right, 31.31 feet high.